Welcome to our EOL seminar. We've moved things around a little bit. It's a different kind of Tuesday. We normally have them on the first Tuesdays, but we like to take the opportunity to welcome people whenever they're available. Come on in, Sean. And also just a plug that next week on Tuesday, Dave Edwards from ACOM. Now I never remember what it's changed into. We'll be giving our next seminar. So we're pleased today to have Jim Edson visiting. Jim spent some time in Pennsylvania like I did. Got his bachelor's degree in physics from Dickinson College, now Dickinson University, I understand.
Oh, they didn't tell me that.
PhD in meteorology from Penn State with our esteemed Chris Farrell as his advisor. After that, he did a postdoc at the École Nationale Supérieure Mécanique, close, sort of like that. And after that, went to Woods Hole Oceanographic Institute, where he was for 14 years, before then moving to University of Connecticut and being there for 11 years. And now he's the head of the Marine Sciences Department. So we should all hail Jim. I don't have too much on. Jim's been involved in tons of stuff, field work, committee work and stuff. I got to know him when he was on the Boundary Layers and Turbulence Committee for the AMS. So with that, I'll have you go ahead.
Okay, so oops. Okay, got it? All right. So for this audience, it's going to be a little bit more of a wonky talk. There'll be a little science at the end, time permitting. But I wanted, actually just threw this slide up just to sort of motivate, well, let's start with outline. So the talk today, I'm going to talk a bit about the methodology of motion correcting fluxes. I'm going to talk a little bit about the Core 3.5 update, was the update for the drag coefficients in Core. And then some current work towards Core 4.0, which has to do with the heat transfer coefficients. Time permitting, I'll talk a little bit about the surface heat budget and the MJO capacitor as part of the DYNAMO program, and then a summary. And just as a bit of motivation, this is a slide from a talk I just gave at the International Ocean Vector Wind Science Team meeting. It was in Portland last week. And this is sort of what's going on right now out in oceanography. And a lot of this is driven by the Ocean Observing Initiative. And hopefully some of these assets will remain after they deal with the decadal survey. But what I'm showing here is two of these spots, actually these three, were field experiments where we deployed surface moorings to measure fluxes directly using direct covariance technique. Some of these other locations in the Erminger Sea, this is the Pioneer Array just south of Connecticut actually, Argentine Basin, Southern Ocean, and up here this the Endurance Array up off of Oregon, are all going to have direct covariance measurements being made real time. The idea is that this could go on for at least 5 years, so we'd have a record of 5 years of surface fluxes. I'm working with Meg Cronin to try to get a flux package on Station Papa. And we've been talking with Meg also about trying to salvage some of the tau array and putting direct covariance measurements in some of those moorings as well. So as you can see, there's a lot going on. And the Ocean Vectors Wind Science Team was interested in this because scatterometers naturally, they report U10, U10N, U10 neutral. But really what they are is they're stress meters, right? They're measuring the surface roughness, which is more closely aligned with surface stress than surface winds. And so it's a very nice way. We're probably not going to develop new models for scatterometers, but it's a very good way to validate results. So there's a lot going on. And so here's what Chris and I have been doing now for decades, really, is going out to sea and making these measurements on ships. Occasionally we'll put the hese spar out, and more often now we're putting these packages on buoys. And these, on each of these platforms, I've got circled in red a direct covariance flux package, which is mainly made up of a sonic anemometer. But if I wanted to zoom in a little bit on what we're actually doing at sea, we deploy 3-axis sonic anemometers. To do the motion correction, we also deploy 3-axis accelerometers, angular rate sensors, and a compass. These we put into this equation to take a measurement, this measurement here, UOBWST, that is being measured on a buoy or a ship or something that's bobbing around in the ocean. So you can imagine if you're, say there's just old seas, you've got swell present but no winds. Just the motion of the buoy itself is going to generate what looks to be winds, and it's really just motion. So we need to first remove that from our measurements before we can compute the fluxes. Now, what I'm going to focus on right now is that term here. This is the transformation matrix. This has Euler angles that you're probably familiar with, pitch, roll, and yaw. And how we determine these angles is through a method known as complementary filtering. Now, complementary filtering, this is a spectra right now with a number of lines on it. What we're actually looking at is a couple of things here. Let me just show you this. I'll get ahead of myself a little bit. So the way that we compute the angles, the Euler angles required for the motion correction, we use angular rate sensors for the most part in this region. So we're just integrating angular rate sensors. However, angular rate sensors have a nasty habit of drifting off when you look at low frequencies. And so the way that we take care of that is we actually use the accelerometers, because an accelerometer, if it's just upright, is measuring gravity. If you tilt it, you're tilting components of gravity into the 3 axes. So for the low frequency component of a buoy motion that's just sort of rolling up and down with the waves, some component of the spectra is just of the accelerometer signal is due to tilts, just buoy tilts. This part of the accelerometer signal is actually measuring the motion of the buoy. And where we put our accelerometers is up near the sonic anemometer, so they're actually sensing also some of the angular rates up there. So the trick is to determine what we choose for this cutoff frequency. And you can see we're picking a range where it really doesn't matter whether we use tilts from the accelerometers or tilts from the integrated rate sensors, right? So for years now, we just sort of picked, we had, I think, one comparison with flip when we started this all out in the late 90s. And we've never really done a rigorous test of this motion correction to date, until now. And here's what I'm going to talk about a little bit first. We managed to convince NSF, finally, to give us a little bit of money to deploy this buoy upwind of this air-sea interaction tower that we built for the Sea Blast program. Okay, so this was specifically designed for turbulence measurements. You can kind of see that you can only go so far with the direction of the wind around here, but it's got a pretty good look angle. And so this tower, we actually deployed a mast that hung a sonic anemometer at about the same height as this sonic anemometer in the buoy. So we have fluxes from a fixed tower downwind of fluxes that we're making on this buoy that require all the motion correction. And just so you can, I don't know if you can see where we're at here. This is Martha's Vineyard right here. Actually, this is the south shore of Martha's Vineyard. Pretty pricey real estate. I think we had to convince like the CEO of Oracle and David Letterman that it was okay to build this tower. We just had to explain what we were doing. They're pretty nice about it. So that's located here offshore of Martha's Vineyard in about 15 meters of water. Okay. And this is, it can be very casual here. We don't have a big audience, so you can interrupt at any time. So here's what we did. All right. So what we wanted to do first was determine the optimal cutoff frequency for this particular setup in hopes that we could apply that to all sorts of cases. What I'm showing here is the RMS difference between the tower fluxes and the buoy fluxes, okay? And what's interesting here, a couple things to point out. This black dashed line is the RMS difference you would get if you didn't do any motion correction at all, right? It turns out that if you pick a cutoff frequency, or this is a cutoff period, just 1 over FC, that is too low, say, a couple of seconds, you can actually do worse than not motion correction, right? So at about, say, 5 meters per second, though, this really plummets. So the RMS difference gets quite a bit smaller. There is a minimum here that we think may be a minimum because it's cancellation of some errors. So we've chosen to sort of go on the safe side, and for the comparisons I'm going to show today, we're going to pick this cutoff period of 12 seconds. I don't know what 1 over that is, but that would be the cutoff frequency, where we have this sort of minimum, there's a minimum, but it's pretty close to the minimum RMS difference, and then it doesn't change much as you go out to longer cutoff periods. So here's what we get. Here's just a scatter plot between the measurements on the tower, that's ACIT, and the measurements on the buoy. This is completely uncorrected. There's a bit of scatter here that is reduced after motion correction using that cutoff period of 12 seconds. Okay, so of course we would have liked to have gotten more high wind data, but this is what we got. Now this data we're going to make this data readily available to people that care about this sort of thing, that would like to work on their own motion correction algorithms, and we welcome that. All right, so you could come up to me after the talk if you want to find out how to get at that. What's a little bit more interesting perhaps is here's spectral plots where we've bin averaged them into various wind speed bins. I don't know if you could see it. The lowest is 0 to 3, 3 to 6, 6 to 9, and 9 to 12 meters per second. So, and you can guess which direction that goes. So the highest winds have the largest fluxes, obviously. And this is that case where I said you could actually make it worse. So if you pick this cutoff period that's too low, you're treating the actual accelerations driven by the motion of the buoy as tilts. And that messes things up. You end up with this big spike in your co-spectra. As you go down to 6 seconds, it gets smaller. And at about 9 seconds, which was close to that minimum value, it goes away. And then after that, it's very hard to see any difference in these fluxes. Another thing just to point out here, it's easier on this frequency plot. This peak right here is the resonance frequency of the buoy, right? So we have reduced that. We haven't completely removed it. But it actually turns out it doesn't have a big impact on the fluxes. So I'm going to zoom in now on this is now for that tau sub c is 12 seconds. These are the co-spectra from, the thin lines are from the tower and the bold lines are from the buoy. And over here, should be near and dear to Steve's heart or Ogive's. So we do a pretty good job of closing the budget. You can see that, however, I cleverly made a little circle to draw your attention to. There is some residual motion here. And when you integrate under the spectrum, it tends to go away, but you can see its impact here. So it seems like no, and that's a good point, because that's a very good point, because I've been seeing these sort of peaks since we started doing this when I look at the co-spectra, and you always kind of said, well, maybe that's swell, because swell can add, so normally obviously the momentum flux is down from wind to waves, driving waves and currents, but there is a portion of that wave spectra which is moving faster than the wind, so you have wave-driven winds, that could reduce the spectra, right? Because you can actually drive, that component of the stress is actually driven upwards, right? Does that make sense? Right? So swell can drive a positive momentum flux. So if the swell is moving faster than the wind, then you can actually drive a flux upward. And we're saying, oh, there's evidence for that here. But you do not see that on the fixed. There's quite a bit of swell that propagates into this region. Not at this time of year though. It wasn't as swell-dominated as, say, in the summer when we get these situations. So what to do about that? It's not clear we need to do anything about it if we're getting the flux right? So let me just move on to sort of think about one reason why we may be seeing this, an artifact of the motion correction. For example, I've made this schematic where, so remember, the buoy is sitting still and the waves are propagating by, but I just moved the buoy along the wavefront. And what you see is if the flow is sort of potential over these waves and then sort of decays with height, down here near the wavy boundary, the buoy is following the flow, right? But the motion correction algorithm thinks that it's being heaved up and down, right, relative to fixed earth. So we may be overcorrecting in these situations. We're inducing a correction for heave that's not really there. The anemometer on the buoy is not seeing that relative wind difference that you would see if you're riding on long swell like this. Right? Well, so here's the deal with that. I gotcha. Here's the ship, right? So the ship is it's gonna smooth out some of these waves. It's a big ship. But also just the fact that it's up here at, say, we're down at, say, 4 meters on a buoy. The ship is up here at, say, 18 meters that's a typical height, I think, on the Nor, 16, 18 meters. So you're actually up here where the streamlines are flattened out, and there's no, I made up these lines, so don't hold me to the lines. But you could imagine that on a ship that's heaving up and down, you are moving relative to the streamlines up there, and so the motion correction is really required on a ship. So two different cases. Things get different as you get closer to the surface, right? So there may be less of this relative motion as measured by the sonic than the motion correction thinks there is. So that's one thing that we're working on, and I was going to try to show a correlation technique we're working on, et cetera, but let me just say this, that the comparison of the momentum fluxes show good agreement with the fixed tower, but the largest uncertainty is at low winds, particularly over old seas. Right? So this induces this residual wave-induced effect under these low wind conditions. And Byron, I'm glad Byron came, because we're working on methods to see if we can't remove some of this this residual wave effects by looking, for example, just the residual correlation. So after you've done your motion correction, if there's still a strong correlation between the waves and your measured wind, or the accelerations in your measured wind, you can remove that. The only issue with here is that you may also be removing real wave-induced stress. That's why I'm kind of always hesitated just to do this brute force correlation approach. But now I'm starting to think we may be justified in doing it because of the buoy measurements. The other thing is just, what does the mean when you're in normally you're on a tower, the flow is quasi-horizontal, and you can just, you average for over 10, 20 minutes, and that's your W bar, for example. And that takes into account all sorts of things that are real, the tilt of your sensor, et cetera. Well, now we're in this wave-following coordinate system. What is the mean in that coordinate system? Right now we just take it as whatever the anemometer measures as the mean, just like we do on a ship. Is there a more sophisticated approach than that to do these covariance measurements? So these are just some things we're working on, and this data set's going to be very helpful to try these various techniques out.
That's nearly at a constant height above the water surface, right?
Well, not if, for example, we're introducing this fictitious correction. So now we have this undulation that's not real, and we're taking the mean of that. I mean, the other thing that sort of saves us is that motion. If it's potential flow, there shouldn't be any correlation for the co-spectra, so that should be negligible. So we don't exactly know about this. And a lot of this is just to make the co-spectra look pretty. The covariance that we measure agrees quite well with the fixed tower and has agreed quite well with all sorts of other measurements in the past. So, but we're working on this because we're always trying to refine the technique. So let's just see how we use these fluxes now for things like momentum exchange. So what I'm going to start out talking about is bulk aerodynamic method. That's one reason why we go all this time and effort to measure these fluxes, is to improve these bulk aerodynamic formula, which are used when you don't have all this sophisticated equipment on a buoy, or over the ocean in numerical models, for example. Those are the two main uses of these bulk fluxes. Focusing first on the drag coefficient. So I'm not going to get too into this, but here's all those these are all the measurements that I had pointed out earlier. So what I'm doing right now, for the drag coefficient at least, is I'm only using the ACES spar, the buoy measurements, and other tower measurements. I'm trying to get away from ship-based measurements for the drag coefficient because they also introduce flow distortion, which is another difficult thing to deal with. So focusing on these sort of low-profile, low flow distortion measurements. Oops, did that already. We're going to attempt to parameterize the drag coefficient. Now there's two things to note in this, the way that we compute the drag coefficient. So first of all, the drag coefficient is defined here as the correlation between the horizontal wind and the vertical velocity. Right? So that's our momentum flux, kinematic form of the momentum flux. And we're dividing by the wind speed squared. And ideally, this wind speed is measured relative to water. Right? That's the wind speed that we want. When we parameterize this drag coefficient from these measurements, a couple things that we have to be aware of. One is the stratification effect, the stability effect. And then once we've taken out stability effects using flux profile relationships, which we have sort of validated over the ocean, we're left with the neutral drag coefficient, which is only a function of the roughness, the aerodynamic roughness, Z0. So in taking all of those measurements from various platforms, showing them here, so we had, besides ACES and the buoy, we had this offshore tower that you saw in that previous photo of the ACE interaction tower. And for that buoy comparison, we hung it from here. We had an anemometer that was hung at the end of a pole. And then from our old friend, the research platform, FLIP. Right, so those are the measurements that are going into this plot of the drag coefficient. As is often the case, we see a lot of scatter at low winds. This is often also associated with swell effects. But when we do the bin averaging of this, we get a result that looks like this. The solid line here is Core 3.5, which we published, I guess, 2 summers ago now. Core 3.0 prior was this dashed line. And the original large and pond formulation is this broken line here. I think it's suffice it to say that above, say, 12 meters per second, large and pond is too low. And this is about 30% too low out here, right? And yet still there are people using large and pond. This is how we parameterize the flux, so we can take these bin average measurements basically, convert them into a roughness length, and this is the parameterization we're using in Core 3.5, where this is the Charnock relationship. Actually, this is important down here. This is the viscous, the roughness due to just viscous stress, essentially. This is the roughness due to essentially wind waves, and we're using the old Charnock relationship to determine that roughness, where now the Charnock variable is a function of wind speed, and that's what we see here. Right, so that's what's in the core algorithm to produce the roughness length, which we then use to compute the drag coefficient, which we can use to compute a bulk estimate of the stress. So there's the paper that we published. And this is here's the results, right? So we have I'm kind of proud of this plot, I have to say. What I'm showing here is the stress directly measured using the motion-corrected fluxes, or from the tower, just the fluxes themselves. Plotted against the bulk version, the 3.5. I'm trying to remember. And in the past, when we make these sorts of measurements from ships, because the meteorologists rarely have control of the ship, you are sometimes pointing into the wind, sometimes pointing downwind, you're moving around. We throw out a lot of the data. So rarely do we have nice, complete time series like this, like you can get from a buoy. And this particular buoy is very nice because if it's vaned, like this one is, it's always pointing into the wind. That's a very nice attribute of buoys. And typically we can set up these buoys so they have lower flow distortion than ships. Same thing with the buoyancy flux, but I'm going to get to that. So back to this. I wanted to make a point. This is more of a science. So here's my core 3.5 algorithm, and here's large and pond. And I always show large and pond because I'm still trying to get people to perhaps stop using it, but they still use it. What's interesting about this plot is this green line. The green line is the parameterization from ECMWF. And what's really interesting about that parameterization is that it's a function of wave age. They run a wave model at ECMWF, and they couple that with their atmospheric model. And they use the wave model to tell them what the phase speed of the waves are under a given location. And from that, they're able to determine what the wave age is. So swell is old, age, and growing sea or new waves. And so what we see here is that this, now the way that they computed this drag coefficient from ECMWF is they looked at their data set, right? And they looked all over the planet at where the wind speed was within a certain range. And so just like I've been averaged here, they did the same thing. And they took that and they computed the drag coefficient at that wind speed. So you can imagine there could have been a wide variety of wave ages at that one wind speed, but nonetheless, this is what they got. And one of the reasons why I got excited showing this at a conference at ECMWF is that I just showed my result and someone came back the next day with their parameterization and said, wow, that looks really good. So here's just more evidence that this is the drag coefficient rather than that being the drag coefficient. Now, why is it? Why is a wind speed dependent parameterization, which is this, so similar to a wave age dependent parameterization, which is ECMWF? Well, there's a very simple explanation. And it has to do with this sort of messy plot. Bear with me. Again, these are these various data sets. I've also thrown in a shallow water that Jalen is used to. This is for RACEX. I was in, I think, 3 meters of water off the coast of Denmark. The rest of these are the sea blast. The flip is the blue, and the red is CLIMODE. And what we see here is that U star over C sub P is there's almost a linear dependence with wind speed. Or wind speed is almost linear dependent on this inverse wave age here, which means that you can simply fit a curve to all this data, and you can flip-flop between a wave age dependent parameterization and a wind speed dependent parameterization, and you get pretty much the same results. Now, what's going on in that plot, I've added just a couple more things here. This is 1 over the phase speed, right? Remember, this was the friction velocity divided by the phase speed. That's the inverse wave age, right? This is inverse wave age, meaning these are old seas down here, and these are growing seas up here. This is what we typically call the fully developed value of the wave age. And according to this plot, at least, the ocean is rarely fully developed, so either one way or the other. So in this wind speed range, maybe you can make the case that you'll see fully developed seas, but for the most part, the waves are not in equilibrium with the forcing. Right? So I'm plotting now 1 over C sub P here. There's very little wind speed dependence of the phase speed we find. It's just a shotgun blast, right? So really what's giving us that nice parameterization, a nice result, is that the friction velocity is a very strong dependence on wind. Okay, so that's what's driving the show, yes?
Is that CP on everything, or is it just the wind speed?
That's just the peak waves. And there's more sophisticated ways of doing that, but that's usually the number that we have available. It's easy to compute.
The models can compute it for both winds and
They can. And so, yeah, so what we could do with something like this is plot the average phase speed, for example, the spectrum. I haven't done that. And
Also the directionality regulation.
yeah, so the other thing that I did is I purposely ignored situations like this in that parameterization and really focused on open ocean results where the winds, except where it's swell, and again, that's where it could be a mess, the wind waves and the wind were more or less aligned. Right? So yeah, that's another thing that will mess you up is directionality. So there's that, there's this. Now, this has led to yet another hockey stick. You think we'd learn our lesson from the climate community, but Larry Mart is pushing this hockey stick idea. So this is just all that data. I've just made it on a nicer grayscale here. And here I did this for my scatterometer friends. I just plotted this. This is essentially the stress to the 1/2 power, right? So, and all it is more or less a constant that I've multiplied the U star by. So that's the result that we got from this combined data set. That's that just been averaged. And of course, I'm plotting it versus neutral winds, which you should. There is, you do have to correct for stability. And I can kind of toggle through, oops, too far. I think I do this. So that is the unstable conditions are in red, stratified or stable conditions are in blue. You apply our corrections and you get, it collapses. Now, we could probably do a little better with that, but that's pretty good. Now, the other thing that I wanted to point out here is we're not the only one who's looking at this. Like I said, Ed Andreas and Larry have their own hockey stick that they've published. This is their parameterization in the broken line. They're pretty close. I have a feeling that they become even closer if Ed and Larry and company plotted this versus the relative wind speed, which they didn't do. So they did not correct for currents in their paper. Currents matter. I have kind of a nice result here, which is this scatter right here is showing winds relative to Earth. And it's a really nice data set because the buoy for CLIMODE was in the Gulf Stream. In and out of the Gulf Stream. It was right near the northern wall. And because of meanders of the Gulf Stream over 15 months, sometimes it was out, sometimes it was captured in an eddy, and for the most part it was in the Gulf Stream itself. And so you get meter and a half currents typically over the Gulf Stream. And so what I'm showing here is currents that are greater than or equal to 1/2 meter per second are in red, and currents less than or equal to 1/2 meter per second are in blue. So in the Gulf Stream, out of the Gulf Stream, just to simplify things. And so when you plot this, though, versus the wind relative to the ocean, it collapses. Right? So it is important to correct for surface currents. Even, I would say, when you're out of the Gulf Stream, look at the blue symbols are out of the Gulf Stream. And there's a systematic bias to lower drag coefficients if you don't correct for currents. And that's simply because when the wind is blowing over the ocean, it's generating a wind-driven current in the direction of the wind, right? So the relative wind is less than your measured wind. So you're dividing by a smaller number and you're getting a larger drag coefficient. Okay, so my guess is that if we corrected for currents in Larry's data set, or Ed Andreas' data set, we'd get even better agreement. The agreement was pretty good as it was. Now, one last thing is, why do we care about all this stuff? Here's one why we care. So this is sort of known space, right? And so here's the core 3.5 algorithm. And this is just a composite of a number of different from drop wind sondes, trying to get aircraft low enough to measure the stress directly. A lot of this is from Powell, and some of these other points are from Sea Blast Hurricane. And you can see there's a pretty big discrepancy between these two. And this is out to about 23 meters per second. Now, what we're finding, and so for a long time, people are trying to, now almost like they didn't accept this because everyone knows that the drag coefficient has to roll over at high winds to get realistic hurricanes, example. Because if it doesn't roll over, you have too much drag, you're applying the brakes too hard, and you can't get a hurricane to spin up. Well, as people have refined their hurricane models and gone to higher resolution, for example, just had this talk with Shui Chen at that meeting, they're finding that they want this to extend out. And more people are finding they get better results with a higher drag coefficient. And so what the community is asking for now is, please help us. We need to have some sort of consensus data or consensus parameterization that allows us to go from 0 to say 50 meters per second. So that's something that we're working on. We have to somehow convince these people out here that, one, they need to maybe jack this up a little bit, and that it doesn't necessarily have to roll over like this. Any questions on that? So there's just another motivation.
Yeah, didn't you say that the number rolled over because they didn't get the hurricanes?
In the old models. So, yeah, exactly. So it's just when they used a drag coefficient, for example, if they used Largen Pond and just let it extend out, they wouldn't get realistic hurricanes, right? But now they're finding, no, we get realistic hurricanes, and we don't like it rolling over. What did Shui say? Shui said that if you reduce the drag coefficient this much, you sort of release the hounds, and you get an unstable circulation. So it's trying to spin up too fast. So they need more drag. Give me more drag. So that's the latest. And Isaac Guinness is another person who's heavily involved in this sort of thing. He also feels like, and he's actually the one that asked me first, could you guys try to come up with a consensus parameterization that extends out to higher winds? But then again, what is the consensus? There's no measurements out here, so it's kind of hard to say. Believe us, if your model works better, but that is one thing. That's what we have out there. But really, we need clever people to try to figure out how to get these stress measurements at higher winds. I don't know if high winds got out much. Yeah, and even that would be wonderful if we had 30 meter per second drag coefficients and they were up here somewhere, say. Huh? They are.
Well, they're from a ship.
Yeah, they're from the ship. So anyways, that's something we're working towards. How am I doing? So heat exchange, next. So this again is the tower versus buoy measurements. You can see that it's not quite as bad uncorrected. This is for the heat flux, W prime, and this is T sonic prime, which is like a buoyancy flux. So that's it uncorrected. This is it corrected. Looks a lot better, and the spectra are much better behaved. So there's no pressure term in the heat budget. So you might expect that the heat fluxes, the co-spectra of the heat fluxes, would be less influenced by wave effects, for example. It's funny, we still see this bloody resonance peak. And I don't know if that's the sonic temperature, which is really based on velocity measurements, being impacted by the resonance frequency of the buoy. I don't know. But all in all, that looks pretty good. I will point out, way back when, and that was CLIMODE, I guess, in 2006, because of the processors and the power required to run the processors on the ship, we could only run at 5 hertz. That's as best we could do. Well, processors have gotten faster, and they've also lowered the power. So, and so you can see we're not capturing all the flux here using a 5 hertz sampling frequency. The tower went out to 20 hertz, was sampling frequency of 20 hertz. So we're pushing hard to have all these buoy measurements made at 20 hertz so that we can capture this flux out in the tail. All right. So given that, I'd like to look a little bit now at the transfer coefficients for heat. The coefficient for sensible heat being the Stanton number, and for latent heat being the Dalton number. Again, we're going to measure this directly, divide by the measured air-sea temperature or humidity difference to come up with these transfer coefficients, which allow us to relate the fluxes to bulk measurements of wind speed, temperature, and humidity. So same thing, we have a stability correction. There's a gustiness correction that we have to apply. And here's one way to get the gustiness correction. It requires measurement of the inversion height. I think Ludo, there he is. I don't know, how many of you know Ludovic Bartow? Chris does. He's the man. We launched tons of balloons during Dynamo to get the inversion height. And what we're going to use those with is our direct covariance measurements of the buoyancy flux to get this gustiness parameterization that we use in core. So we have a couple of data sets where we can fine tune what we've been using for many, many years now. But what I'd really like to focus on for this talk is, again, the thermal roughness length, Z0 Q. So again, so we're going to now plot our measured, say, latent heat fluxes versus these bulk differences to compute an estimate of the transfer coefficient. And that's in this plot. And so I'm going to go step through this. It's kind of cool, the story that it's going to start to tell. So I'm going to show you a number of different field campaigns, results from field campaigns. Most of these now are ship-based, right? We have a feeling that the heat fluxes are less influenced by flow distortion on ships, so perhaps these are a little bit more robust measurements. And so this is from the DYNAMO experiment, and what you're going to see is the name of the experiment over here, and whether it's the transfer coefficient for humidity, which is the E, evaporation, you want to think of it that way, and also the transfer coefficient for buoyancy, CB, which is the buoyancy flux you get out of a sonic anemometer. And then below is the bin average. And I remember the first time I did this during analysis of Dynamo, I said, it's not matching very well with Core 3.0. Well, then I just started to add, so that's the buoyancy flux from Dynamo. That's the Dalton number from CLIMODE, buoyancy flux from CLIMODE. You can see down here, these are the bin average results. You can start to see a pattern. Very recently, we had a SPURS program. That's a NASA program. I don't know if you can see the magenta. It was in the trade, so it rarely got up above 10 meters per second. And also the evaporative coefficient during SPURS. And so what I'm going to do next is take all that data, just bin average it. These are now the standard deviation of all that data. And guess what? I'm proposing a new coefficient that looks something like that. Now, this is not the first time that we've seen this sort of behavior at high winds. And I'm really looking forward to high winds data set, so if you see something like this. In FastX, that was the parameterization that they came up with. So this is sort of the range, very high wind experiment in the North Atlantic. So they at least saw a decreasing transfer coefficient. So what's going on out there? We don't know, I don't think. Sea spray, the original formulation, I think from Luke Katsaros and Businger, see this behavior as well. And I think they attributed it to sheltering of the waves.
The inflection point is where the right there.
When white capping start, yeah.
It's like that one. Well, the spray would connect to
Yeah. So they'd go in different directions, and I see it's similar behavior at those wind speeds. So that's sort of a nagging question, but an interesting question. And there was a recent high wind experiment where they measured all of these fluxes, so it'll be a good test to see if we get general agreement. We'll tease something out. Have it. And then the other thing for the WRF community, maybe in the audience, if there's some WRF users, this is the parameterization that's in the default version of WRF. And I noticed that it was higher than Core 3.0 when I first started playing with this. And by the way, I've learned that it's not enough to just publish your results and then expect them to find their way into numerical models. That rarely happens. The way that happens is to get involved in some numerical modeling. So we have a couple of good ones at UConn now. And so I'm starting to put core into those models and see we actually have a paper, we're preparing a paper that makes it, looks like it's worth the effort. You get better results. But anyways, this was the parameterization that I think originated in MM5. That's, like I said, the default version of WRF. And it actually agrees quite well with these latest measurements up to about 14 meters per second, and then it continues to increase. So again, this is the way that we parameterize it in core. This would be core 4.0, this blue line. You can see basically a constant roughness length does a pretty good job of estimating the transfer coefficient, and this is at low winds. This is a roughness Reynolds number here. So this is lower winds and then a decrease at higher winds, and we're still trying to figure out what the cause of that is. But a fairly simple parameterization that mimics that behavior. All right, so I think I'm doing pretty good. I wanted to talk a little bit about the surface heat budget and some of the results that we had in Dynamo. So when I was at Woods Hole and sometimes when I'm at UConn and Marine Sciences Department, the only thing the oceanographers really want from me is the net heat flux that warms or cools the ocean, this term, and the surface stress, those two things. So those are the two important components of ocean modeling. And so what we have here is the up and down welling solar radiation, up and down infrared radiation, the latent heat flux, and the sensible heat flux. You add those all up, and depending on how you define the sign convention, if it's, say, into the ocean, you would expect the ocean to warm, and if the flux is out of the ocean, and that's the sign convention I like, the ocean is expected to cool. So we're going to focus on those two for this talk. But here's just some nice time series. So this is from the DYNAMO experiment, which was the dynamics of the Madden-Julian oscillation experiment. We were stationed in the Indian Ocean, just south of the point of India on the equator, for approximately 3 weeks per leg. I'm going to focus on the best leg, because that was the leg I was on, in the middle, where we actually saw 3 different MJO events. Well, 2 different MJO events, and the jury's still out as to whether that was a separate MJO event. And sort of what this is showing us here, do I have the net heat flux? I really should have daily averages on this. But focusing in on this component here, the MJO, as it propagates around the globe, in the Indian Ocean, there's a suppressed phase where there's very strong solar insolation, not a lot of clouds, spotty rain, and the ocean is warming. So you have a lot of solar radiation that's overwhelming the heat fluxes, mainly the latent heat fluxes. Yeah, you have a question? So warming of the ocean, and then you have the active phase of the MJO. When it goes over, then all hell breaks loose, strong winds, larger fluxes, lots of clouds, a lot less solar radiation, and cooling of the ocean. And actually what I'm showing down here is that this is the energy input. This is what you would get if you integrated this time series. It would look something like this. And so we can see that there's an increase of energy into the ocean, it levels off, and maybe starts tipping up. Increase during the suppressed phase, loss of energy, and then again another suppressed phase. This is why we like this one so much. It really does show a nice cycle of the MJO. So I think I have another, nope. So here's the deal. This is now just the surface heat flux. So the heat flux the net heat flux going in or out of the ocean. There's obviously, if you look at a box model, there's other terms. There's advection of heat both in and out. If these two are roughly, if there's not a lot of advection, then it's mainly driven by the net heat flux in the top, and then some of the radiation escapes through the base of the mixed layer. So that not all of that solar radiation that's penetrating into the ocean contributes to warming of the mixed layer, right? Some of it penetrates all the way through and is essentially lost to the mixed layer. So this is something that's really important to consider when you're looking at whether or not you would expect the ocean to warm or cold. Yeah, warm or cool.
So you're showing that it's kind of a residual.
Yeah, it's a sum of all those terms. Don't call it a residual. No, but it kind of is, yes.
So what's the last term? Sensible
Oh,
rate
rain.
Oh,
So there's a contribution to the sensible heat flux from rain, and we do include that in the core algorithm, and it's included in this. Those are the black lines. It's very sporadic. It can be large, but it's really sporadic. So it contributes some. It's important to include, but it's not driving the show. Okay? Any other questions? All right, so here's just a conceptual model. I've been learning as I've gone along about tropical meteorology. I was not a tropical meteorologist when I started, and I'm still not, but I'm learning more every day. This was sort of the conceptual model that people had proposed for the various phases of the MJO as it moved across. So this is essentially the suppressed phase, active phase, and sort of a recovery phase. And these are the measurements. And so these are from Raywinson measurements. So this is the specific humidity measured by the balloons as a function of height. And I believe what I'm showing here is the red and the blue. I'm trying to remember. It's these two lines. So it's I think the red is, actually it'll make more sense once I show this. Right. So the red is during this phase, and it's drying into this phase, right? Over here, in this phase, it's moistening, and then this phase, it's again drying. So the three panels are representative of these three sections of the passage of an MJO. This is the SST for the conceptual model. So you can see that most of the cooling in the conceptual model occurs during this latter phase, right, according to the conceptual model. However, you can see pretty clearly that at least the boundary layer response to whatever's going on does agree fairly well with the measurements. Right? Now, there's a lot going on here, and what is driving the changes in these profiles is the local evaporation from the sea surface. But it's part of what's going on. Simon DeZerka has done a ton of work on this, and I'm going to pretend to be Simon. But what we found is that while the surface evaporation directly beneath this MJO event is important consideration, it's really moisture convergence aloft that is driving a lot of this variability from stage to stage. So without moisture convergence aloft, you cannot explain the amount of precipitation that falls, right? So there's way more precipitation than local evaporation at this site, and the same thing was seen in the Togakor data set. So it has to be coming from somewhere. Of course, evaporation has to play a role, but it's more on a larger scale. That evaporation is moistening the boundary layer, and then various mechanisms are causing it to converge, in this case, over the equator as an MJO event goes across. So what I'm going to focus on instead is the response of the ocean, because I usually give this to oceanographers. So what they would say is that when we're in this active phase, right, underneath this plot, there should be no change in the sea surface temperature. And actually what we've found, and that would be consistent with these black lines here. These black lines are showing the location of these phases, okay? So that being the case, you can see that between these black lines, which would be between these black lines, the ocean is clearly cooling, and it's not steady state underneath the active phase. And so the one thing that we propose, so that's according to our timeline where these various phases would transition, and really your model, the conceptual model just needs to say, all right, during this phase is when the ocean is cooling. Under the active phase of the MJO, you have significant cooling of the sea surface temperature. So that's that. Now, I remind you that we're measuring this, and we need that if we want to look at the ocean's response to this heating. And so here is just the net heat flux and the integrated net heat flux over time in November. Suppressed phase when the ocean is warming, active phase when the ocean was observed to cool. And so what we had, I forget what this guy's name was, but he was a hoot on the boat. This was the guy whose job was to measure the transmission of solar radiation through the mixed layer. So we actually measured that, we quantified that. And it turns out it was about 25% of the incoming solar radiation on average went through the base of the mixed layer. So you only kept about 75% of the solar radiation. And if you account for that, if you subtract that off, that 25%, now you begin to see a pattern like this in our integrated energy flux, where during the suppressed phase, we're charging the ocean, and during the active phase, we're discharging the ocean, at least in terms of this simple energy budget that we've come up with. And you can kind of see that here. Ocean is warming. When the energy is being discharged, ocean is cooling. And I know that someone is working on this. I haven't seen whether a simple model like a 1D ocean mixed layer model can mimic this behavior with that amount of solar radiation being lost. And here's the difference between 3.0 and 4.0. A little bit more charging and a little bit more discharging with this proposed parameterization, or 4.0. So just a hypothesis we're working on, that the initialization and strength of the MJO convection in the Indian Ocean is at least partially governed by the oceanic storage of energy during the suppressed phase and release of this energy during the active phase. And one thing that you could maybe look into to look at this hypothesis is whether a weak MJO, which doesn't suck all the energy out of the ocean as it passes over, is then followed by a stronger MJO because there's some residual energy left in the ocean. That would go sort of part and parcel with this hypothesis. And that is something we have long enough records to see if that's the case. So, summary. I think I did pretty good. First part of the talk, the comparison of the direct covariance and momentum fluxes do show good agreement with a fixed tower. The largest uncertainty is at low winds over old seas, and that holds for both the direct covariance fluxes and also the co-spectral behavior. That's where we see that largest bump. So a significant component of these recent field programs have, I don't know if that's English or not, but we've been trying to improve these parameterizations of sensible and latent heat. And you can see the data is being used to investigate boundary layer response to air-sea interaction. And there's a workshop here this week. It's the year of the maritime continent. Did everyone know that? It is. We're going to have a party. So there's a workshop here, YMC, Year of the Maritime Continent, that will take place tomorrow, Thursday, and into Friday, I believe, here at NCAR, for those of you interested in Madden-Julian oscillation, those sorts of things. It's basically, we were in, I don't know if you've ever seen the MJO, so they break it down into slices of a pie, where the Indian Ocean is one slice, and that's where we were centered during DYNAMO. The next slice over is the maritime continent, and that's the Indonesian archipelago, where the convection moves over it, is clearly modified, the convection, I think it weakens, passes over the maritime continents into the Toga Core region, and often re-intensifies. And we're trying to get a better handle on that slice of the pie in this Year of the Maritime Continent. And with that, I'll take any questions.
Thanks, Jim. Further questions?
Yeah, Jim. I'm just wondering if you think we should be using the same value of FC or tau for correcting the ship data as you found for the buoy data.
Yeah, I've actually found that you could go to longer, make sure I get this right, to longer periods. So right now, for the buoy, we're using 12 second as a cutoff period. I typically go to 30 seconds on the ship. All right. But you can see, I could have gone out to 30 seconds with the buoy. It just seemed to, one reason why I went shorter is because it tends to reduce the uncertainty of low winds again, if you go shorter. The longer time scale, if you have a strongly forced seas, you can kind of you can go out to 30 seconds. You just don't want to go so far out that the drift from your angular rate sensors become an issue.
Right.
And 30 seconds, it's not an issue.
And I know we also see this residual peak in the corrected spectra on the ship, maybe at 0.1 hertz, a little lower frequency. And the only way to get rid of it was the decorrelation.
Yeah. So I think the ship is moving up and down relative to the flow. The other thing and on the buoy too, because there's one thing about saying that a buoy typically has less flow distortion than a ship, but you can design a buoy with an awful lot of flow distortion. I actually found that out in SPURS. So you have to be just as careful on a buoy to sort of move your anemometers away from blocking structures, et cetera. But the idea on a ship is that if you've got a lot of flow distortion up and over the bow of the ship, and it's pitching and rolling, you're kind of you're rolling that flow distortion on wave time scales into your spectra. So it could be that as well. But I also think it's real. Even at ship height, you do see wave-induced perturbations in the mean flow.
Questions?
Jim, back to your hockey stick plots.
Yes.
There's that break point at order 5 meters a second.
Yeah.
Can you physically
Yes.
provide an interpretation of that and what you think it is? Meaning,
I believe I can.
left or right of that?
Almost there? There we go. Let's do that one.
Here it's 9 meters a second, 8 meters a second.
Yeah, so here's my interpretation of this. So there's a range of wind speeds. So down here at low winds, the viscous stress is driving the show, right? So you're physically dragging, the atmosphere is dragging the ocean along, and it's generating this viscous stress at these wind speeds. As you move out into higher and higher wind speeds, it becomes a mix of fully rough seas and this viscous. The viscous stress and the wave-induced stress are contributing to the total stress in this region. There is a region, and I've always thought of it in this, right around here, where the sea becomes fully rough. And basically that means is that the roughness elements, the waves, start to poke their heads all over the place through the viscous sublayer. So this behavior is consistent with a fully rough sea. This down here is viscous, and then there's this transitional period. I actually had another line at one point that was the transition from the viscous stress to fully rough sea.
So at 5, let's say, meters per second, the ocean's not rough?
It's rough, but it's a mix. So you can still see the surface, the viscous sublayer. And so this one, I think. Whoop. Where was the roughness? Yeah. But that roughness Reynolds number plot was for the viscous? I will. Oh, it's at the very end? Oop, that was it. Right there.
So the upper one, the roughness rule. The wind zone guys say rough, the transition from smooth to rough occurs at roughness rule. Can you do it?
And we're saying it's going beyond that.
Okay, different.
Well, it's, the bump on the lower one is a 12 meters a second.
Yeah.
And that's up at roughness rule.
Yeah, right. I think I've actually plotted that, the wind speed versus the roughness Reynolds number, and it didn't jive with, Alejandro did this. Yeah, so we're seeing this transition. I don't know if this corresponds to 12 meters per second. Presumably it does, right? And it's at a much higher roughness Reynolds number,
So
closer to
the
8.
LKB parameterization peaked at 1, as I recall.
Yeah, and I think
But it was not Z naught Q, it was RQ. It was Z naught Q times U star divided by nu,
Yeah.
which made it peaky.
I think if I were to plot LKB on this, it would do something like that. It would transition earlier
Yeah.
to lower values.
So to me, it's surprising that 4 is so different from 3.
And we shall see.
Yeah.
Yeah. Yeah, because it's, for me, it's what's going on out here. The high wind data set's going to help with that. But we have an awful lot of data in this regime. I don't know. We shall see.
We actually running a little bit late, so
On that note,
I think we'll stop.
very good.
But anyone who wants to stick around, I'm sure Jim would be happy to entertain questions informally.
Yep.
Thanks.
Thank you.